Welcome to this week's lab. Today we'll be talking about prediction, using data about what's happened in the past to try to understand and predict what's going to happen next. We can do that intuitively, right? We do that intuitively almost every single day. When you get out of bed, you are generally going to predict when you turn the light switch on, your light will turn on because that's happened over and over again in the past. However, when we get to more complicated patterns, it's very difficult, if not impossible, for the human mind to actually process those types of predictions. And so we can rely on models to do that for us. As in every other case, this means that we are going to be abstracting away some data. We will have to limit the amount of data that our models look at. And so we're stuck in this world where we have to build the most effective model we can that's reducing the data down to something that's manageable, but is still retaining information that's helpful for prediction. First and foremost, let's go ahead and pull in the data set we want to use. We're going to do this in a slightly different way than we've done in the past. So here what we're going to do is we're going to download a zip file using Python and extract that zip file using Python. But we're going to do it with a data stream, which means that we aren't actually going to copy the zip file to our local hard drive. We're just going to open up the files that are within it. So first, let's do a few imports. So we're going to import requests, import zip file, and import IO. These are just the three modules that we'll be using for this data request. And the data set that we'll be using is a data set from a tool called GeoQuery, which is a tool that allows you to download satellite information for counties and districts around the world. So for example, you might get a data set from GeoQuery that tells you the satellite measured number of trees within every county in Virginia. That's one way you could use that tool. What I've done in advance of this video is I've used that tool, and again, you feel free to use it. It's located at geoquery.org, but I've gone ahead and done a request where I've downloaded information on conflict in Africa. So we're going to be using a wide set of variables to predict kind of 1 year's conflict in Africa, how much conflict will occur, specifically looking at deaths by conflict. So the zip file for that pre-built URL is located here. So zip URL equals and then I'm going to go ahead and copy and paste this, but then I'll show you where we can get this URL from as well. So if you go to the datadoctor.io, the website that has a lot of the data sets and videos for this class, on the left you'll see data sets. So if we click on that, and then you'll see Lab 5 Prediction GeoQuery Data. If you right click on this and you click Copy Link Address, that is how you can get the link address for this particular data set. You can also click on this, left click on this, and download this zip file and look at it on your own computer if you want. So now we have that URL. We're going to go ahead and define what's called a download request. So we're going to tell Python to download the file located at that URL. So we'll do download equals requests.get zip URL. So this is just the URL where that zip file is. And importantly here, do stream equals true. And so this just tells Python we want to use this zip file without downloading it to our local hard drive. We are then, on the next line, we're going to define the zip file itself. So we're going to do z for zip file equals zip file dot zip file, capital Z, capital F, very important. Then in parentheses, we'll do io dot bytes io, and then in parentheses again, download dot content. So let's work through what this is doing. First, from the zip file module, we are defining a zip file. So the function within zip file that creates a zip file is called zip file with capital Z and a capital F. Then what we're doing is from this package IO, we are saying, which stands for input output, we're basically saying that we want to interpret this zip file as raw bytes. So these are actually the bytes coming in. That's when we set stream equals true, what we're doing. So we're saying don't look at this as if it's a file. Look at the individual bytes of data that are coming into Python. And this lets Python interpret it even though we haven't downloaded it to our local hard drive. Download.content is the actual content that comes from this particular request. So that's how we get this in. This is something that you may want to use in cases where you're downloading lots and lots and lots of zip files, but you don't necessarily want to save all of those zip files. You could also, just as we've done before, download the zip file locally onto your computer, upload it to Jupyter Hub, and open it just like a normal file. But this is just to show you another way you can access data. The final thing we have to do is Z for our zip file, extract all. And so this is going to take the zip file we've defined here and extract all of the data. So I'm going to go ahead and run this. And there we go. So now we've actually extracted that particular set of files. Now, what we want to do is just confirm real quickly that that loaded has how we thought to. So we're going to look at our file structure. So if I'm going to go back here to my Jupyter dashboard, it's fine. And so this is my Jupyter kind of hard drive. And you'll see I have a lot more files probably than you do, but we do have these new files that we have extracted. So we have specifically the zip file that we just got. So let's, if we look at that, we see that the URL we put in was this 5095. So this is the data that we got out of that zip file. And we can see we got two different files. We got documentation.pdf. So this is kind of tells us what is in that CSV. And then we got the actual CSV itself, which contains the data. So this is the file that we're going to want to open in Jupyter, because again, this is the CSV that we're most interested in. So I'm going to copy this, and I'm going to go back into my Jupyter notebook. Let's take a look at the specific variable that we are going to be trying to predict. So just to plant an idea in your head, we're going to be building a model based on 2012, and then we're going to predict into the future of 2013 based on our 2012 model. So the idea is we want to make our 2012 model kind of as accurate as possible for 2012 before we then apply it to 2013. So the specific column that we want, let's take a look at our data frame. And then we are going to grab the column UCDP deaths, and it's called 171.2012.sum. And again, if you look in the PDF that came with the zip file that you downloaded, you can see how I knew that this was the appropriate column to pick. So I'm going to click Run. And this is the actual values that we see in that particular column. So this is for 2012. You'll remember from the last video, every single one of these rows is an administrative unit in Rwanda. Now, one thing that immediately jumps out here is that there's a lot of zeros. In fact, everything I can see is a zero. So one of the first things I need to do before I do modeling like this is to confirm that I have meaningful data, that there's actually some places in Rwanda that experienced greater than 0 deaths. So to do that, what I'm going to do is do a quick count to see how many times that's true, actually subset my data. So let's do df, and then another bracket, and then here greater than 0. And so you'll remember this from earlier videos. We're actually going to select all of the rows of data for which this column is greater than 0. So I'll go ahead and run this. And here we go. So these are the 9 rows of data that there was more than 0 deaths. So these are the actual cases that we're trying to predict out of the 2,000 or so rows. So it's very, very rare that we have a recorded conflict event in Rwanda in 2012. So we want to be able to predict something that's a fairly rare occurrence, which is very, very challenging, and you'll see that borne out in our accuracy assessments later on. So there are, as I mentioned, 2 models we're effectively building here. One is 2012, so predicting 2012 with 2012 data, and then one is 2013, so trying to extrapolate our findings from 2012 to 2013. When we look at the accuracy of our 2012 model that we're going to calibrate with, that's referred to as internal validity. So how accurate is our model for 2012 when we use 2012 data? Once we fit that model using 2012 and we apply that same model to 2013, then we'll be talking about external validity, or the validity when we look at something that's outside of the scope of the data we use to calibrate with. So let's go in, and first we're going to focus very, very heavily on just internal validity. So getting our 2012 model as accurate as we can. So we'll we'll go ahead and get started here. So the first thing that we want to do is we want to actually build a data frame that allows us to go in and kind of make sense of the data. So we only want to use some variables that we believe might be most relevant for the prediction of conflict. You'll remember if we look at the entire data frame, there are many, many, many variables that may not make any sense to include in our analysis. For example, the name. There's no reason for us to believe that the name of an administrative unit and the number of deaths would be correlated. These are just text. There's no numeric. So we need to think through for every single one of these cases, all of these columns, does it make sense to include this column of data in my particular model? Now, what I've done in advance is I've gone through all of these column names, and just as a reminder of how you can do that, you type in df.columns, and it'll give you the list of every single column name. What I've done is I've gone through these, and I've tried to pick out a subset that are meaningful for this type of a problem. So just to give you, and again, you can look at the PDF to learn more details about these, but this is the amount of vegetation. So this could be, for example, how successful crops are. This is nighttime lights, which is a good proxy of electrification and poverty. We have air temperature and precipitation, which again could be correlated with agriculture. Elevation, distance to roads, very important for economics. And then this Afrobarometer question, this is a question that it's how many people trust their government. So there's a few different varieties of that question. And then finally, an estimate of GDP for each kind of subnational boundary. So I'm going to be using all of these to try to predict conflict in 2012. That's my goal. So I have all of these defined. I'm going to go ahead and run this. And first I need to subset my data frame so it only includes these columns, because those are the ones I'm going to be using for my prediction. So let's do df, we'll call it 2012 equals df.dropNA, subset equals column names. So the first thing we're going to do is drop all of the rows of data that don't have any values in any of these different variables. And then let's go ahead and define our all of the variables we're going to be using for prediction. We'll do is x2012. That's going to equal df2012 column names. So just to reiterate, first we define all of the column names that we want. Then we drop any rows that don't have measurements for those particular columns. And then finally, we create a X data frame. So this is our predictors, everything we're using to predict. And that's just going to equal our data frame, but only the column names, only the columns that match these column names. So go ahead and run this. And if I run now, let's look at x2012. You'll see it's basically the same thing, but we now have many fewer columns. We only have 10 columns of data. So we can see all 10 of those columns are the same columns that we just specified a moment ago. So all of these different columns of information. Now we need to define what we are actually going to be trying to predict. So this is a little bit more straightforward. We'll do y2012, and that's going to equal the data frame 2012 that we just created. And then the column that we want is UCDP deaths 171 2012.sum. So I'm going to run this dot 2012.sum. And then we'll run y. And so this again is that numeric indicator of if a death occurred. Now we actually want this, instead of being a number, right? Right now this is 0.0, 1.1, there's numeric representations. We actually want this to be just a straight binary true and false. So to do that is fairly straightforward. We just want to do a quick test. So we're going to say, okay, anytime there was at least one death. So anytime that value is greater than 0, call it a 1, otherwise call it a 0. So this way, if there's 10 deaths, it'll just be counted as 1. That is, a death occurred here or not, the probability that conflict is occurring. And then at the end, we do @asType int. And what this does is this alone will return a list of true and false, the words. This will convert true into 1 and false into 0. So this now y2012 will be this set of binary values. So we'll go ahead and run this. And then we'll take a quick look, and it should look very similar. Yeah, so now we have all just zeros and ones, and they're no longer floats, right? It's just 0.0 or 1.1.0. This is our data frame. We're going to be using X to predict Y. And let's go ahead and focus again on the 2012 internal validity first. We want to see how well we can use data from 2012 to predict in 2012. To do this, we're going to actually use a neural network, so kind of a flavor of what you've probably heard termed as deep learning. We're going to be using a fairly reduced form version of a neural network that will run reasonably quickly on your Jupyter environment. So to do this, let's go ahead and import. So we'll do from sklearn.neuralnetwork import MLP classifier. This stands for a multi-layer perceptron, which is kind of the detailed version of one class of neural networks. We now have to define what's called the structure of our neural network. Don't worry about this at all. You can play with these parameters if you so desire, but kind of in general, these are the types of parameters you would learn a lot more about in a machine learning or applied machine learning class. But for now, we'll just define our MLP as the MLP classifier function. You have to define hidden layer sizes. And again, don't worry too much about this. We're just going to put in some values here. Just go ahead and copy what I'm putting, and random state equals 16.3. Then we have to fit our neural network. So this is actually how we train this particular neural network. So let's type in mlp.fit x2012.values and then y2012.values. And that's how we actually create the or train this particular model. And then we actually need to create our prediction. So once we've created and trained our model, we have to create the prediction of values. Now in this case, we're going to be using 2012's model to predict 2012. That will allow us to test the internal validity of our model. How well does our model work for predicting 2012? So our prediction in this case is going to equal mlp.predict, and then we're going to predict with our 2012 values. So I'm going to go ahead and run this. Equal sign there. Go ahead and run this. And this will take a moment because neural networks do take a little bit of effort to create. And then let's take a look at our prediction. So if I just copy prediction down here, you can see this returns an array which is all zeros or ones. So you'll remember our y2012 variable. So if I paste this and run this, that was all zeros and ones. So our prediction is the exact same thing. It's trying to classify every single place as a 0 or a 1. However, remember there were very, very few places that actually had conflict. And so let's take a look and see how many places our model actually predicts will have conflict. And so we can do that by printing the sum of prediction, because it's just all zeros and ones. 0. So 0 places were actually specified as, likely to have conflict in our model, which is not particularly helpful. So what we want to look at instead of just the raw prediction is the probability that conflict would occur in every single location. So we don't just want the binary conflict or not. We actually want to look at underneath the hood what probabilities the model set for every single location. So that 100% probability would mean the model absolutely thought that conflict would occur. 0% would mean the model thought there would be no conflict. So let's look at probability prediction, we'll call it, and mlp.predict prob. And again, x2012.values. So almost identical to this, except here we're using mld.predict proba, which gives the probabilities. So we'll run this, and this again will take just a moment to refit the model. And then we'll just take a look at this variable that was just returned. And so here you see, this is an array that is returned, where this is the probability the first row had no conflict. So a 99.6% chance that there was no conflict in the first row. And then this is the probability that it did have conflict. So a very, very low probability. These two values for each row will add to 1. So there was a 100% chance there was either conflict or no conflict. One way we can assess the internal validity of our data is to look at the probability that we predict in cases where there was conflict as contrasted to no conflict. So what we would want to see, if our model was reasonably strong, we would want to see the probability of conflict occurring be higher, predicted to be higher, in the places where there was conflict. So let's take a look. First, we're going to just briefly convert this back into pandas. So we do class prediction and accuracy. So you'll remember these are the two values. So there's the 0 and the 1. We actually need to convert these into two different categories because we really only want to know this value. This is the probability we're estimating for conflict. So we're going to extract really just this one value. Don't worry too much about the programming here. You will learn the details of what's going on here in your Python CSCI 141 or other related course, but this is how we can extract that particular type of information. So this will actually give us two new variables, class prediction and accuracy. So I'll run this. So all we really want here, and the reason I've called this accuracy, is this is the value that we really care about. The second value tells us, is what we're going to use to determine if the places that experience conflict actually had higher levels of conflict. So to do this, we're going to create our own kind of custom pandas data frame here. So I'm going to say accuracy data frame, and that's going to equal a panda data frame. So this is how we create a new pandas data frame. Then we'll do another zip. Don't worry too much about the details here. And what this is going to do is this is going to append. So to our original Y2012 data frame, this was the list of 1 or 0, where 1 indicated conflict occurred and a 0 indicated it did not. We're going to add to that this value of accuracy. And then we'll go ahead and call these. We're going to name them prediction and truth. So we're going to have one column, which is our Y2012 column, which is either a 0 or a 1, which is if conflict occurred or not. And then we're going to have another column, which is this accuracy variable we're calling prediction, which is this variable right here. It's the probability that our model ascribes to conflict occurring. So we'll go ahead and run this, and let's actually look at this data frame. And here we go. So you see there's these two different columns where we have our model's estimate of the probability that conflict occurred, and then the true estimate from the actual 2012 data. We want to summarize this to get an idea of, in the cases where there was conflict, was our predicted value higher? Is our model ascribing a higher probability to areas where conflict truly occurs or not? So to do that, let's do a group by. So we'll print from our accuracy data frame .group by truth.mean. So we're saying go in, and for every single time truth is 0, and for every time it's 1, report back the mean of those two groups. So we'll run this, and here we go. So this is the actual result. So across all of our model, for every single one of those districts in row 1, if in reality in 2012 there was no conflict, our model is ascribing, roughly a 0.25% chance that there would have been conflict. Conversely, if there truly was conflict, our model is ascribing a 0.43% or 0.44% chance that there was conflict. Obviously, this model is not particularly strong. We are trying to predict something that's very difficult to predict, but at least our model, in cases where there truly was conflict, we are predicting a higher probability of conflict occurring, kind of on average. So that's looking at 2012 alone. What we'll do in the next video is start actually looking at how you would use this model and apply it to predict the future in 2013.